Alright, this next video shows how we use Gauss's law to derive the expression for an E field, electric field, nearby a very large charged plane. So there's two other videos in this series, the sphere and the line. This is the third and final one. And these are all just supporting what you maybe already see in the textbook, because these are derived that way too by the author, and in fact probably every textbook has that. So the first thing I'm going to do here is draw a very large plane of charge. And I can't draw it as large as I'd really want to, wouldn't have enough space for that. We'll put some positive charge on here, evenly spread out. And something that's important to know about a charged plane is it has not an actual Q number, an amount of charge, but it has what we call a charge density. That way, if the plane is infinitely large, we don't have the problem saying how much charge is on an infinitely charged plane. So in Dr. Knight's book, he uses the Greek letter beta. Kind of looks like an N. I've seen a lot of textbooks that use the small case sigma, so you just have to get used to whatever you're seeing, depending on who's watching this. And so what we want to know is if we put a dot, let's say just a little above the surface, like there, it's right above the middle of the sheet, how strong is the electric field there? So like with all things in Gauss's law, you have to start by drawing a Gaussian shape. So our Gaussian shape is going to match the symmetry of the electric field. Now the electric field in this case is nice and uniform. And you have to know going into it that it's uniform, because if you don't know that, you really shouldn't be using Gauss's law at all. So if you could picture field lines, you draw some field lines here, these blue field lines, they would be, you know, going up like that, and it's hard to draw this in 3D, but all evenly spaced out. And we would also have these same field lines down here, trying to draw a little bit of perspective so you can get this sort of 3D effect. That's not too bad. You'll find better pictures with these textbooks because they have high-priced graphic artists that make them all. So now I'm going to draw a Gaussian shape that is near those, and I usually do this in a dashed black line. So get my black pen here, and what you want to draw is some shape that goes right through the middle of the sheet, or I guess the sheet goes right through the middle of it, and I usually draw a Gaussian cube. So it would look something like this. There's the top of the cube, and then down here, it pierces through. Boy, this is really a lot that's drawn on here. So it looks like it stops right there at the sheet, but that's only because you can't see the underside of the sheet. And so you would have the same kind of cube down here. And does that look like it's piercing through the bottom there? You would see all four sides. So it's like somebody impaled a Gaussian cube right through the middle of the sheet. Okay, so I'm going to draw maybe some lines. Since we can see through this thing, I'm just going to draw lines like that. Almost looks like two cubes, but it's really one. Okay, so let me get ready to write our Gauss's law equation. There's a symbol for the flux. That's the sum of all the little electric fields times all the little areas through which those fields are piercing. And then we have all the charge inside that Gaussian shape divided by epsilon sub naught on the other side. So we do Gauss's law with problems with enough symmetry so that we can say that the electric field is going to be uniform over any particular surface. So if we look at the top surface of this Gaussian shape that we drew, you just have to say, all right, is there any reason to think that the field at one location there is any different than at any other location? And with a uniform field, it shouldn't be. And that same is true for the bottom base here. So that means we can pull this out, and all we have then is the total area through which that field is piercing. Well, I'm going to shade in here all the area that it's piercing. That would be this, and we've got field lines piercing that. Notice they do not pierce through the sides of the box because the sides are actually parallel to the field line. So they skim along it, but they don't pierce it. So that means if we call this area A, we actually have 2A for the total area being pierced, top and the bottom. Now what do we have on the other side? Well, we've got to look at how much charge was actually enclosed when we drew that Gaussian shape. Remember I mentioned that this eta number here is the charge density on the sheet. That means how much charge per unit of area. Well, our box was big enough so that we have one area's worth of charge inside the box. So let me shade that in red. This is the surface right here that actually contains charge. Notice, because it's a nice, it's not really a cube, it's a box, but it's got the same dimension of that area that it has on the lid or on the base. And so we can just substitute, get my right pen here, substitute in eta times A for the amount of charge that's inside there. And then we put that over epsilon sub naught. So when we solve this for E, which remember is what we're after, we're going to be able to cancel out the A's, and we are left with eta, the charge density, over 2 epsilon sub naught. And that is the expression for the electric field somewhere near the surface. If you get too far away, then you got to worry about this not being an infinitely big sheet. But if we keep the sheet big enough, or if we keep ourselves close enough to the sheet, like that little green dot I had drawn, then we can say that we have a nice uniform field and it's just this big. Notice the big thing about these sheets is there is no dependence whatsoever on where you are around the sheet as long as you're reasonably close. So we're going to wrap it up there. We've gone about 7 minutes and I think that's just long enough.